how would you know if a large language model was lying to you? If you give ChatGPT a certain phrase and ask it to forget the phrase, it will claim that it has. However, since the phrase is part of the model's context window, this is actually impossible. And if you badger ChatGPT enough, it will admit that it actually does still know the phrase and repeat it back to you. Although we can and do train our AI assistants like ChatGPT to be helpful and honest through specific examples, we have no direct access or control over model concepts or behaviors like truthfulness. This problem of LLM interpretability is an active area of research. One of the most promising approaches involves extracting model features using a separate learning algorithm called a sparse autoencoder. These extracted features often correspond to human understandable concepts like cats, dogs, Wi-Fi networks, and more complex concepts like internal conflict. Remarkably, once we have a feature, we can increase or decrease its strength in the model it was extracted from. If we increase the value of the internal conflict feature in Anthropic's Claude model and ask it to forget a phrase, it will immediately admit that it can't actually forget words. Examples like this are compelling, but as one of the key authors of this work, Chris Olah, has pointed out, we've only been able to extract a tiny portion, likely less than 1%, of the concepts that we know large language models must know about. Chris uses a great analogy here. The features we haven't been able to extract yet may be a kind of dark matter of interpretability. Feature extraction gives us a telescope, allowing us to see the brightest stars in the model's universe. We may be able to build better and better telescopes and fully understand what's going on in large language models. Or it might be the case that a significant portion of what these models have learned can only be observed indirectly. But why is it so difficult to understand how these models work in the first place? Why do we need to train a completely separate model to begin to make sense of what a language model has learned? Why can't we just train these models to be understandable in the first place? Why are we only able to extract a tiny portion of all model features? And why can't we just scale up sparse autoencoders to peer deeper and deeper into the universe of language models? Let's follow the path of some text through a large language model. We'll start with the phrase, "The reliability of Wikipedia is very," and see if we can make sense of how the model decides what to say next. We'll use Gemma 2B, which is a scaled down version of Google's Gemini model. First, each of the 6 words in our phrase is converted into a token from Gemma's vocabulary, and each token is mapped to a vector of length 2304. These vectors are stacked together into a matrix of dimension 6 by 2304, and passed into the first layer of Gemma. Each layer of language models like Gemma consists of an attention and multi-layer perceptron compute block. These compute blocks return new matrices of the same size as their inputs. So after passing our 6 by 2304 input matrix into the attention block in our first layer of the model, we get back a new 6 by 2304 matrix. We then add this matrix to our original input matrix, and the result becomes the input to our next compute block. The output of this block, again a 6 by 2304 matrix, is added to our input, just as we did before, completing the first layer of Gemma. This output is then passed into the second layer of Gemma, which does the exact same thing, just using different learned weight values. We repeat this process again and again, with Gemma incrementally transforming its input matrix layer by layer into a new matrix of the same size. This matrix we keep updating by adding the outputs of each compute block too is called the residual stream. After passing through all 26 layers, to figure out what Gemma is going to say next, we just take the last row of the final matrix and map it back to a word. Interestingly, to do this, we multiply the last row of our final matrix by an unembedding matrix, which results in a new vector of length 256,000, where every entry corresponds to a single token in Gemma's 256,000 token vocabulary. This vector is interesting, because after normalizing with a softmax function, it gives us the probability, according to Gemma, of each token in Gemma's vocabulary occurring next. We can rank these tokens by their probabilities and get a sense for what Gemma thinks about the reliability of Wikipedia. The most probable next token is the word important, with a probability of 20.21%. We can get Gemma to expand on this by appending the vector for the word important to our original input, and passing this new slightly larger matrix through Gemma to find the next word in the sequence. Repeating this process, we see Gemma giving a nuanced take on Wikipedia, as we would expect from a well-tuned model. However, the next word choice of important was only assigned a probability of 20.21%. And Gemma's other probable options lead us down very different paths. With a probability of 11.16%, Gemma will tell us that the reliability of Wikipedia is very high. Or Gemma could go the other way and tell us that the reliability of Wikipedia is very low, questionable, or poor, with probabilities of 10.8, 9.48, and 5.47% respectively. These lower probability options are important, because production systems generally do not just pick the most likely next token. This often leads to uninteresting or unhelpful responses. Instead, next tokens are sampled from a modified version of the model's probability distribution. So in practice, this version of Gemma will give us different takes on the reliability of Wikipedia. Some nuanced, some positive, and some skeptical. Now, note that so far we're not using the instruction-tuned version of Gemma. This final version of the model includes a number of post-training steps to better align Gemma with the behaviors we expect from an AI assistant. Interestingly, if we switch to the instruction-tuned version, this increases the probability of measured takes, such as the reliability of Wikipedia is very much a topic of debate. There are still skeptical takes that Gemma could deliver, but they are less likely after instruction tuning. Post-training steps like these used to tune Gemma have proven reasonably effective at shaping the behaviors we want from AI assistants. However, these techniques do not give us direct control or understanding of specific model behaviors. A more direct approach is to open up the model itself and try to figure out exactly which parts are creating specific behaviors. Where exactly in Gemma's 2 billion parameters, spread across 26 layers, has Gemma decided that Wikipedia is reliable or not? A recent wave of these efforts, popularized under the name Mechanistic Interpretability by Chris Olah, has made impressive progress. Let's apply some ideas from Mechanistic Interpretability to our Gemma model, and see if we can make sense of what's going on. Putting together the Gemma walkthrough for this video required a ton of hacking. On projects like this, I really value uninterrupted focus time, which this video's sponsor Incogni has really helped me with. As a dad of 2 young kids, my phone generally needs to be on. Legit stuff comes up all the time, but spam calls and texts can be a huge distraction. A couple of months ago, when I was considering working with Incogni on this video, I signed up for an account, and I couldn't be happier with the results. I'm getting far fewer spam texts and calls, and more uninterrupted focus time. The way Incogni does this is really impressive. After signing up for an account, you give Incogni permission to work on your behalf to contact data brokers to remove your data, which brokers are generally legally obligated to do upon request. From here you get this great dashboard that tracks all the removal requests and progress. It's really impressive. My data has been removed from 115 separate data brokers so far. This would be incredibly time-consuming for me to do manually. In the United States, we also have these people search sites, where for a small fee, anyone can look up information about you, like your address, email, phone number, education, employment history, social media accounts, and so on. It's pretty wild. I signed up for an account on one of these sites. It's crazy how much information I was able to find on my wife, who I have not yet added to my Incogni account, which I will be doing. They have a great family and friends plan. By comparison, after being an Incogni customer for a couple of months, impressively I wasn't able to find any records of myself on the same people search site. You can get a great deal on Incogni, 60% off an annual plan, by using the code Welch Labs, or following the link in the description below. Plus it helps me continue to make great content. Huge thanks to Incogni for sponsoring this video, and helping me take back my data from data brokers, and get more quality focus time. If Incogni sounds like a good fit for you, please check it out. It really helps me out. Now, back to the dark matter of AI. Let's apply some ideas from Mechanistic Interpretability to our Gemma model. To get a better sense for how these techniques work, let's visualize our text as it passes through the model. Recall that our 6-word prompt, the reliability of Wikipedia is very, is converted into a 6x2304 matrix, and each block of Gemma adds a new 6x2304 matrix to this matrix. And this modified matrix is known as the residual stream as it moves through the model. After the final layer, the last row of the residual stream is converted back into a token, and becomes what Gemma says next. Let's visualize this final row of the residual stream as it moves through the model. Visualizing a vector of 2,304 floating point numbers is a bit tricky. Let's rearrange our vector into a 48 by 48 matrix, and visualize each number as the intensity of a pixel in an image. to hopefully make it easier to spot patterns in our data as it moves through the model. Before our first layer, our vector looks like this, with a few large positive and large negative values that stand out in our image. Note that we don't have to wait till the end of our model to map this vector back to a token. At any point, we can normalize this vector and multiply by our unembedding matrix, as we would at the end of the model, to see what token our vector represents. Generally, this vector would correspond to the word vary, with a probability of 100%, because we haven't done anything to our input matrix yet, and this last row of our matrix is just the mapping or embedding of the last word in our phrase, which is the word vary. However, this version of Gemma uses a soft cap function before producing final probabilities, which limits the model's confidence in any single next word. Interestingly, the effect here is for the model to predict variants of the word vary, including different capitalizations and even different languages. Let's see how Gemma's first compute block changes our embedding vector image. The output of the attention block in the first layer of Gemma looks like this. And when we add it to our residual stream, it now looks like this. If we map our new vector to a token, we don't see much change, with variants of the word vary now being predicted with slightly different probabilities. So if our model was only composed of this compute block, the next word predicted would be the word vary, so Gemma would tell us that the reliability of Wikipedia is very, very. And we do often see word repetition like this in smaller or poorly performing language models. Adding the output of the multi-layer perceptron block in our first layer to the residual stream, our vector now looks like this, and still maps to variants of the word vary. We see similar behavior all the way through the 15th layer of the model. Note that this does not mean that nothing is happening in the first 14 layers. Remember that we're only visualizing the last row of our residual stream matrix, and our residual stream is changing, just not enough to flip our top predictions yet. Around the 21st layer of the model, we see for the first time expressions of doubt or skepticism, with Gemma telling us that the reliability of Wikipedia is very questionable, with a probability of 9% after the 21st layer. Perhaps we can isolate some doubting or skepticism behavior in this layer. Having a close look at the output of the multi-layer perceptron block in the 21st layer, we see large values at the indices of 1393, 1945, 257, and a few others. Each of these locations corresponds to the location of a single neuron in this layer. Maybe one or more of these neurons has learned to capture doubt or skepticism. One simple way to test this idea is to directly modify the values of each of these neurons, and see how it impacts the model outputs. If we take neuron number 1393 and fix its output value to -160, this is about twice its observed maximum, and pass our text through our model again with this modification in place, our final outputs do change, with high moving up in the rankings. If we reverse our intervention and clamp our output to +160, we see our trend reverse, with low, questionable, and poor moving significantly up in the rankings. So increasing the output of neuron 1393 in layer 21 increases Gemma's trust in Wikipedia, and reversing its outputs increases its skepticism or doubt. So have we found a specific Gemma neuron that controls trust, or in reverse, doubting or skeptical behavior? Another way to test this idea is to search for other examples of text that cause neuron 1393 in layer 21 to output large values. If we found a doubting or skeptical neuron, then the text that causes this neuron to maximally activate should reflect this. Searching through 100,000 examples from the PILE dataset, and collecting the examples that maximally activate neuron 1393, these examples seem to have nothing to do with doubt or skepticism, and instead seem to correspond to examples of capital letters in acronyms or proper nouns in various contexts. We've reached our first big hurdle in interpreting Gemma. Clearly this neuron has some bearing on the model's doubting or skeptical behavior, but the examples that this neuron responds most strongly to are related to a seemingly unrelated concept. This phenomenon of single neurons in large language models corresponding to multiple seemingly unrelated concepts has been observed across a broad range of models, and is known as polysemanticity. Interestingly, polysemanticity occurs much more frequently in language models than in vision models. Specific neurons in vision models have been shown to respond uniquely to things like faces, cars, and many, many more recognizable concepts. In 2022, Chris Olah and the team at Anthropic published an interesting hypothesis to explain this observed polysemanticity. The idea is that language models are able to learn more concepts than they have neurons, essentially by representing concepts using specific combinations of neurons. The team calls this idea superposition. So concepts may be spread across multiple neurons and layers in Gemma. If we can't isolate concepts and behaviors to certain layers or neurons, how can we hope to understand or control language models? One option is to modify the model architecture, to encourage or force the model to have fewer neurons fire for any given input. Ideally, this would stop the model from spreading concepts across multiple neurons. The Anthropic team tried this in 2023, and found that models still exhibited polysemanticity, even in extreme cases, where they forced only a single neuron to fire at a time. Another option is to try to figure out which combinations of neurons respond to certain concepts. Perhaps neuron 1393 in layer 21, combined with other neurons, will cleanly represent the concept of doubt. But how can we possibly figure out which combinations of neurons map cleanly to which concepts? Remarkably, there is a simple model that we can train to learn these mappings, called a sparse autoencoder. If the superposition hypothesis is true, we should be able to take some combination of the outputs of the neurons in a given layer, and this combination of neurons should respond very strongly to a single specific concept, and respond very minimally to all other concepts. Most sparse autoencoders used today in mechanistic interpretability work by hooking them up to a specific point in the model, such as the output of a certain layer or the residual stream at a certain location. So if we take the output of the 21st layer of Gemma, where Gemma started exhibiting doubting behavior, the idea here is that we can take these 2,304 neuron outputs and find some combination of these outputs that cleanly responds to examples of doubt. We can take a single combination of our outputs by multiplying our neuron outputs by a new weighting vector of length 2304, where each entry in the weighting tells us how much of each neuron output to take. We can then add these results together to give us a final output value that should correspond to the overall strength of our concept. Now, per the superposition hypothesis, our model represents more concepts than it has neurons, so we need more than 2,304 of these weighting vectors to tease out all the different concepts. Let's try modeling 16,384 different concepts, so we need 16,384 separate vectors. We can stack all of these weighting vectors into a single new matrix of dimension 2304 by 16,384, where each column represents the contributions of our 2,304 neurons to each concept. Multiplying our neuron output vector by our weighting matrix yields a new vector of length 16,384, where each entry should correspond to the strength of a specific concept. Now, how do we learn the weights for our new matrix that will allow us to cleanly map neurons to concepts? For any given input example, we know that we only want a very small number of our 16,384 concepts to be active at once. Otherwise, we would run into the same polysemanticity issue we saw with neurons. This is where the sparsity comes in. Sparse autoencoders work by forcing most of the values in our concept vector to be 0 or near 0, and then using the remaining values to reconstruct the original input. Reconstruction of the original input consists of mapping from concepts back to neuron values, which we can do by multiplying by another weight matrix, this time of dimension 16,384 by 2304. So our sparse autoencoder works by mapping our neuron outputs to potential concepts, better known as features, by multiplying by a weight matrix, and then forcing most of the values in the resulting feature vector to be 0 or near 0, and then taking these few remaining outputs and mapping them back to neuron outputs by multiplying by a separate weight matrix. If the superposition hypothesis is correct, and our sparse autoencoder is working well, then our output should be a reasonably faithful reconstruction of the original neuron outputs. Sparse autoencoders are trained to minimize this reconstruction loss. Let's see how sparse autoencoders apply to our Gemma Wikipedia example. The Google DeepMind team recently released a project called GemmaScope, which includes over 400 separate sparse autoencoders, trained on data from various locations in the model and across variations of Gemma. Let's take the sparse autoencoder trained on the outputs of the 21st layer of Gemma that we've been working with. Let's pass in our example text into our model, pass the output of our 21st layer into our trained sparse autoencoder, and see which elements in our concept or feature vector are activated. We can visualize our feature vector in the same way we visualized our embedding vectors, by reshaping it into a 128 by 128 grid, and displaying it as an image. As expected, our feature vector is much more sparse than our embedding vectors. Now, let's see if we can make sense of the concepts or features that our sparse autoencoder has learned. A challenge with sparse autoencoders is that we don't know ahead of time what actual concept any given element in our feature vector corresponds to. We can see that features 7344, 8353, and 8249 have high values for our Wikipedia example. But what concepts in our text are these features responding to? As we did with individual neurons, we can get a sense for what individual features represent by searching for examples of text that maximally activate a given feature. Part of the Gymoscope project includes launching on a platform called Neuronpedia, which allows us to quickly see what examples maximize any feature in any sparse autoencoder released with the Gymoscope project. Looking up feature 8249 for our sparse autoencoder, we do see many examples of text where questioning or uncertainty are expressed. We can also amplify or reduce this feature's impact on the model, just as we did with individual neurons. Clamping feature 8249's output to a constant value of 100 impacts Gemma's next word prediction as expected, increasing the probability that Gemma will tell us that the reliability of Wikipedia is questionable. We can ask Gemma to generate more text with our modified feature in place, and see that the steered version of the model is highly doubtful and questioning of Wikipedia's reliability. If we crank up this feature to a constant value of 500, we see that Gemma starts to just babble, mostly with variants of the word question. So by learning to map neuron outputs to sparse features, sparse autoencoders are able to recover human understandable features that respond consistently to specific concepts in text, and can even be used to control model behavior in predictable ways. Sparse autoencoders have been applied to a range of language models with impressive results. In 2024, the Anthropic team showed that features extracted from Claude 3 Sonnet are even multilingual and multimodal. A feature for the Golden Gate Bridge responds to references to the bridge in multiple languages, and even to images of the bridge. The Anthropic team has scaled up their autoencoders to extract around 13 million separate features. And a team at OpenAI has trained a 16 million feature autoencoder on the GPT-4 residual stream. However, as Chris Olah has pointed out, these millions of features appear to just be scratching the surface. The Anthropic team has found features for specific neighborhoods in San Francisco, but the Claude model these features were extracted from knows way more granular information about the city, like the intersections of streets, which do not show up in the extracted features. Large language models appear to know far more concepts than we've been able to extract so far. We may be able to simply continue scaling sparse autoencoders as we've scaled language models, but there are a number of theoretical and practical obstacles that may block this path. It's possible that the computational cost of extracting extremely rare features will become prohibitively high, leaving these rare features as an unobserved dark matter that has to be observed indirectly. The current sparse autoencoder paradigm effectively focuses on a single location in the model at a time, leaving it incapable of disentangling cross-layer superposition. There's work actively underway from the Anthropic team and others on a new approach called sparse crosscoders to address this issue. Finally, as the number of features increases, the features become more and more fine-grained, making them more difficult to work with. You can see this directly when experimenting with large autoencoders on Neuronpedia. Searching for doubt, we find many features, and it's not clear how various choices will affect the model until we test them. Sparse autoencoders and other mechanistic interpretability approaches have given us incredible insights into large language models. It will be fascinating to see how far we can push mechanistic interpretability, and if the capabilities of large language models will continue to outpace our abilities to understand them.